Hello everyone and welcome to the next webinar series. I am Aparna Deshmukh, Technical Director with Next, and I will be your moderator for today's session. We are eager to learn all about our today's webinar titled Synthetic Fibers in Concrete, Types, Applications, and Design Considerations. The PDF of this presentation can be found in the handout box. You can use the PDF to follow the presentation and take notes if you desire. You may use the question box to ask questions during the webinar, and a speaker will be happy to address them at the end of the presentation. For continuing education credit, attendance for the entire duration of today's live webinar will earn you a certificate of completion for 1 PDH. Your certificate will be available in ACI University under the Certificates tab within 2 days. For those who cannot join us live, the on-demand recording will be made available about a week after the live presentation. ACI is an approved education provider for the American Institute of Architects and the International Code Council, and this webinar has been approved for 1 learning units. Please take note of our disclaimer on the screen for the next webinar series. Let's get started with a short description of our today's webinar. The webinar will focus on providing an overview of various synthetic fiber types, the application, and offer practical recommendations for design and specifications. Additionally, it will highlight key ACI documents relevant to fiber-reinforced concrete, serving as valuable resources for practitioners engaged in designing fiber-reinforced concrete elements. Our learning objectives for this webinar are as shown on the screen. Let's welcome and introduce our today's speaker, Dr. Mark Rashid. Dr. Mark Rashid is a senior structural engineer at Master Builders Solutions, where he serves as a technical resources to design professionals and end users of the company's products and specialty concrete technologies. Prior to joining Master Builders Solution, he worked as an engineer at the American Concrete Institute and Ghaffari Associates. Dr. Rashid holds an MS and a PhD in civil engineering from the University of Texas at Austin, as well as an MBA from the University of Michigan, Ann Arbor. He is a licensed professional civil engineer and a member of the American Concrete Institute, actively involved in several ACI committees, including ACI 544, Fiber Reinforced Concrete. Let's welcome Dr. Rashid and listen to his presentation.
Thank you, Aparna, and thank you for joining us today. In this webinar, we will discuss the use of synthetic fibers. We'll go over types of fibers, applications, design considerations, and more. Now, to begin with, we'll start with an introduction and discuss some of the basics of fiber-reinforced concrete. Then we'll move into discussing the 2 types of fiber-reinforced concrete, or synthetic fibers. In this case, we'll talk about microfibers and macrofibers. For microfibers, we'll focus on the usage of controlling cracking due to plastic shrinkage. For macrofibers, we'll discuss different applications in design, and actually get into more details about this. I will conclude this presentation by briefly going over some adjustments that need to be done with mixes when using fibers in general. I'll also discuss a bit the sustainability of synthetic fibers in the presentation. Okay, to start with, concrete is composed of cementitious materials, water, aggregates, and admixture. Fiber-reinforced concrete is composed of all the same components, except we also add fibers to concrete. Now, fibers are introduced in concrete mainly to improve the mechanical performance of hardened concrete. We don't add fibers for any other additional reason. So fibers are not added to improve workability or finishability. They might affect these properties, but the main goal of adding fibers is improving mechanical properties of concrete. Now, to start with, I'm going to show a video comparing unreinforced concrete, concrete reinforced with wire mesh, and then fiber reinforced concrete, just to give you a feel of what type of performance we get with fiber reinforced concrete. So let me load the first video. Okay, so the first portion of the video on the left is one that's unreinforced. As you can see, after just one hit, the concrete not just cracks, but also splits apart. That's because no reinforcement is there. While in case of the other two, the concrete cracks, the fibers or the reinforcement don't actually stop concrete from cracking, but after the concrete cracks, you do get some post-crack strength or some kind of crack control out of both materials. So to start with, this is the first type of benefit that we get out of using fibers, is fibers provide some post-crack strength to concrete. Now, going back to our presentation, here's a list of all the properties that fibers do enhance. These are the ones that you see on the left. Now, why is this important? Well, if we're trying to design with fiber reinforced concrete, we actually want to know what properties we are getting out of fibers to be able to best use the materials. Now, one of the primary benefits that we derive from fibers, as you saw, is crack control, or what is more accurately, crack width control. In this presentation, I'll probably just call it crack control, but what I'm trying to say by that is that fibers are preventing cracks from opening and becoming wide. So that's why crack width control is the more technical term. Now, you've observed that in the video, and later on I'll show more data on how fibers also improve post-crack flexural strength and also tensile strength. Now, there are other improvements like shear strength and other properties that I have listed on the left. For this presentation, however, I'll focus mostly on flexural strength and not shear, because most of the fiber applications I'll be discussing have a mode of failure that's more flexural as far as design goes, rather than shear. So shear is not something that I'm gonna be covering extensively here. Now, certain properties of concrete are not improved by the presence of fibers. And this includes any type of fiber, whether we're talking about synthetics or steel. It doesn't matter what the shape is, whether the fiber is twisted, whether the fibers has hooks or has some type of embossment or texture. None of any configuration of fiber will help you improve these properties. These typically include compressive strength, pre-crack fractural strength, or what we call modulus of rupture. So this is the strength which cracks the concrete, again, not affected by fibers, modulus of elasticity, freeze-thaw resistance, and among others. Now, to just give more a rationale behind this, we have to think about the fibers as a composite material. So fiber reinforced concrete is basically a fiber composite, and a fiber composite is consists of a matrix material, which in concrete is the cement paste, and then fibers. Now, the fibers in a fiber composite can be continuously and aligned, discontinuous and aligned, or discontinuous and randomly oriented. In the case of fiber reinforced concrete, they're discontinuous and randomly oriented, so it's what you see on the right. Now, for the case of concrete, we already have a composite material which is consistent of paste and aggregate. By adding fibers, we are improving that composite material even further, but just note that the addition of fiber doesn't change the matrix material itself, meaning cement paste is unaffected by the fiber. A lot of the properties which I said are not improved by fibers are dependent on the type of matrix that is used, the cement paste, and are also dependent on the bond between the aggregate and the cement paste. So these properties are not typically altered by the addition of fiber. Also take into account that the amount of fiber we add in fiber reinforced concrete is very small compared to the rest of the materials. Typically, in a lot of the applications I'll discuss, we have 0.5% by volume or less being added. So that amount of fiber does give us some improvements for the composite material, but it's not enough to change the properties which I mentioned are not affected by the addition of fibers. Okay, one other thing is that to remember about fibers is that fibers have a short length. So the most mode of failure that you would expect out of fiber reinforced concrete is fiber pullout. So the use of high strength materials and fibers doesn't necessarily improve your overall performance of concrete. There are limitations because other properties like fiber length, shape, width, the bond between the fiber and the paste also play a role. Now, why is this important? Well, this is important because some people sometimes look at fibers by just looking at their strength, and that's not the best way to look at fibers. You should actually be looking at how well they perform in concrete. Now, to learn more about fibers, there's an ACI committee, which is ACI Committee 544. And before I get into more details about synthetics, just wanted to let you know that this is the best source of information as far as fiber reinforced concrete goes. There's a lot of information out there. If you're looking for something that's accurate and actually contains most of what you would need for design, I would reference you to ACI 544 documents. The committee has over 10 documents about fibers, and there's more that are being created. Okay, now going back to our main topic, which is going to be synthetic fibers. The types of fibers available in the market are either steel, glass, synthetics, or natural. Most use of fibers is typically going to be either steel or synthetics. Now, this presentation, again, is focusing on synthetics fibers, but note that a lot of the applications I'm going to talk about and the concepts apply to any type of fiber. Okay, getting now more into synthetics, the materials which are typically used for making synthetic fibers are listed on the left. So you have polypropylene, polyethylene, polyester, nylon, carbon, aramid, and acrylics. Now, as far as practical use and what's available in the market, you'll mainly find polypropylene fibers being used. And these type of fibers come into two different variants. One is called microsynthetic fibers, or I'll be using the term microfibers, and the other is called macrosynthetic fibers, and I'll be using the term macrofibers. So these two terms are also would be found in documents, and they're mostly what is commonly used in application. Now, as far as the difference between the two types of fibers, you have a difference in the property of the fiber itself. So the length of the fibers are typically different. The macrofibers are going to be longer in general. They're also going to be thicker than the microfibers. The microfibers are usually thin. As far as usage and properties we get out of these fibers, you also have a different usage, and I'll discuss this in more details. Microfibers are mainly used to control cracking due to plastic shrinkage. That's their main use. As far as macrofibers, they're used to replace the reinforcing steel in some application, and they basically have performance that's very comparable to steel fibers. Okay. Now, for polypropylene fibers, you have to meet a certain standard for them to be able to be used in concrete, and that's ASTM D7508. That's the standard for micros and macro fibers, and there's also another category, which I'll mention a bit later, which is hybrid fibers. Now, why are we using polypropylene fibers in concrete? Well, because polypropylene is a very durable material when utilized in concrete. It doesn't absorb water, it doesn't react with alkali, and unlike steel, it doesn't corrode. Now, in the case of steel fibers, for example, corrosion could be an issue, but sometimes coatings are added to the steel fibers to avoid corrosion. Now, in some cases, the corrosions can also be reactive in high pH environment, and that's also an issue that we don't have to worry about when using synthetics and polypropylene in this case. Okay, now let's get into the microfiber portion. and discuss what it's used and what dosages are typically there. As I mentioned, the main usage of polypropylene monofilaments and fibrillated fibers is going to be for plastic shrinkage crack control. Now, the two variants are the monofilaments you see on the left and the fibrillated that you see on the right. So these fibers look different, and they're also used at different dosages. Monofilaments are typically used at dosages from 0.5 pound to 1.5 pound, depending on the performance of the fiber. A fibrillated fiber, on the other hand, is typically used at a single dosage of 1.5 pounds per cubic yard or 0.9 kilograms per meter cube. That's what typically these fibers are used. As I mentioned earlier, they're mainly used for plastic shrinkage, crack control, and flat work. They're not typically used to replace reinforcing steel. Now, there is an exception we see in the field, is that sometimes 1.5 pounds of fibrillated fibers is used in residential slabs to replace a very light wire mesh. But that's an exception that's typically only used in residential concrete and when the reinforcement requirement is very light. Okay, now talking a bit about the mechanism of plastic shrinkage. Just as a reminder, plastic shrinkage occurs before the concrete sets, when the concrete is still in the plastic state. It occurs when the evaporation rate of moisture at the surface of the concrete is higher than the bleed rate of water going up to the surface. Now, the factors that affect evaporation are the ambient temperature, humidity, wind speed, and the temperature of concrete. As far as bleed rate, it is mainly affected by the presence of supplementary cementitious materials, or what we call SDMs, and the water cementitious ratio. Now, to know how effective fibers would be for a concrete mix as far as controlling cracks due to plastic shrinkage, there is a standard test that's ASTM C1579. Now, as you can see in the image, the test attempts to replicate the causes of evaporation that I just talked about earlier. By comparing a concrete mixture with fibers and one without fibers, we can calculate a value that's called the crack reduction ratio. Now, that value is basically employed as a performance measure to evaluate the effectiveness of the fiber product being used or the dosage of that fiber product. As I mentioned earlier, the fiber performance is not just a function of tensile strength. And we typically want to use concrete tests to evaluate how effective the performance of the fiber is, and that's what that ASTM 1579 is there for. Now, in this figure that you see, someone was looking at how the CRR value, the concrete performance, compares to the tensile strength of the fiber. And as you can see from this figure, there is no correlation between strength and performance of the fiber. And that's because, again, the performance of the fiber in concrete is not just a function of the tensile strength of the material, it is also a function of the length, the shape, the size, or overall, you can say the architecture of the fiber. So please keep that as a note. When you try to specify this type of material, it's not enough just to have a strength of a fiber. You have to look at the performance in concrete. And in this case, this is typically the language that you would use for specifying microfibers in concrete. So in this slide, you see an example of language that could be used for a monofilament fiber. And an engineer can set the performance criteria. That's what I have highlighted in orange. So your CRR value can be 40%, could be 80. Typically, we see values between 80 and 90 being specified. And then the dosage is typically recommended by the manufacturer, because the manufacturer should have test data that tells them that 1 pound of their product will reach a value of 90%, for example. So knowing that information, the manufacturer would know what fiber product at what dosage can be used to meet this type of performance requirement for microfibers. For fibrillated fibers, the same approach can be used. The only difference on here, as I mentioned, is that the dosage is typically set at 1.5 pounds. So in this case, it's more about choosing the product that would meet the performance criteria at that dosage rather than trying to determine a dosage as far as fibrillated. Now, as far as microfibers, this is all that I'll be discussing in this presentation. The rest of the presentation will focus mainly on macrofibers. Now, to start with, macrofibers are mainly used to replace reinforcing steel, either full replacements or partial replacements, depending on the type of structure, and I'll get more into the details later on in the slides. Now, as you can see in the figure, there are different types of macrofibers available. So there are different types. They look different. They have different shape other than just length and thickness. They do have a different architecture. So you can see there are stick fibers, tape fibers, and ropes. And even the same types, if you look at this, at the two ropes I have on there, they don't look the same. So this is something important to note about fibers in general, not just synthetics and macrofibers. There are no standard where one product or two different products are going to give you the exact or be the exact the same. There's many different types available, and I'll discuss more how this affects how we actually specify fibers and how we recommend dosages. Now, one more note to mention on here, there is a type that you might see available that's called the hybrid fiber, and hybrids are typically a combination of micros and macrofibers. So they're mostly, could be more than 80% macros, and then they do put sometimes a small amount of microfibers just to improve overall performance of concrete. Okay, now let's get a bit into the applications of where fibers are typically used. Slabs on ground is a very common application for fibers. I'll discuss this one in more details. And I'll say fibers aren't just used for your regular jointed slabs. A lot of the fiber applications in slabs are for jointless slabs. Second application, which actually is very similar to slabs on ground, is pavements, overlays, and sidewalks. We are seeing an increase in usage of fiber there just because it reduces the need for labor, so no steel needs to be set, and it's much easier to build just with fiber reinforced concrete as far as these applications. Concrete slab on metal deck, or what's sometimes called composite metal deck, is another common application of fiber reinforced concrete. I'll discuss this one in more details and provide some information on what the code requirement is for this type of application. Residential basement walls is another application where we've seen the use of synthetic macrofiber mainly for crack control. So a lot of these walls are designed as plain concrete design, and I'll discuss plain concrete design in a later slide. But the usage of fibers actually improve a lot of the performance as far as crack control that even has shown to have performance superior to what is required as far as temperature and shrinkage reinforcement by typical codes for this type of application. Now, footings and foundation is another application where we've seen synthetic fibers being used. As you can see in the picture, there's still a lot of steel reinforcing being used there. That's because the macrofibers can't replace every type of reinforcement. In this project, actually, the reinforcing that was removed was mainly the reinforcement added to control cracking. So it wasn't the reinforcement that was used for increasing flexural strength. And that's obviously because there are limits on how much you can get out of fibers. Now, this example is building foundations. We've seen also application of fibers in smaller type of foundations like residential, where in a lot of cases they are designed as plain concrete with minimum reinforcement, and that's also where fiber can actually work very well. Underground construction and shotcrete is a very common application of macrosynthetic fibers. I won't discuss this topic much in this presentation, but we do see a lot of this being used. Finally, utility precast. So there are a lot of precast elements that are made with fiber reinforced concrete, and this is again something to save as far as labor and as far as cost when it comes to materials and reinforcement. Now, there isn't any specific type that is mainly to be focused on in this presentation. That's why I put the different types of pictures. But I can tell you, as far as application, we go beyond even what you've seen as far as usage of synthetic microfibers. Okay, now in all the applications that you've seen, the biggest challenge is always determining what dosage of fiber is needed, especially when we're looking to replace any type of reinforcing steel. We're typically looking to get something that would give us a very similar performance. Now, as you saw earlier, as far as the pictures I had of fibers, unlike reinforcing steel and mesh, fiber products in the market are not all equal. They come in different shapes and forms, and that actually affects their performance. So it doesn't really make sense to be substituting one fiber for the other or be using the same dosages of these fibers. The best way to handle them is to have some type of performance specification, not a prescriptive one based on purely dosage, a performance one that would basically give us what we need for the type of structure that we had. So when we're evaluating the performance of fibers, we're also looking for some test methods in concrete. Like I showed earlier with ASTM C1579 for micros, we're looking for similar tests that we can use for evaluating the fibers, and typically these type of tests have to be standardized. As far as ACI documents, if you want to learn more about the testing of fibers in hardened concrete, I'd refer you to ACI 544.9, which is a document that discusses mechanical properties of fiber reinforced concrete and the different tests which are available to evaluate the FRC. Now, for design purposes, we won't use every test that's out there, of course. We'll typically focus on a couple of tests that give us the properties that we're looking for. And these type of tests will let us know what dosage of fiber A we would need versus what dosage of fiber B. Again, based on the performance of each fiber and the requirement we have for a certain application. The most common tests used as far as design of FRC are going to be ASTM 1609, which is a flexural performance test. It's a beam test. And then ASTM C1550, which is a test that's done on a disc. This is typically done with shotcrete. As I said, it's a disc-shaped element and it's not a beam. In today's presentation, I won't get too much into shotcrete, so I'm not going to discuss this test much. But if you have any questions on it, please reach out, or you can ask some questions at the end of the presentation. Okay, so the main test that I'll discuss is ASTM 1609, which is commonly used for all other applications other than shotcrete. And as I mentioned, it's a beam test where we measure the load versus deflection. This figure shows you an example of results we get with ASTM 1609. As you can see, when a beam is loaded, it reaches a value where the concrete cracks. The first peak that you see up there is typically what we call the modulus of rupture when it comes to flexural strength of the concrete. And then beyond that point, we typically get no strength if you only have plain concrete with no reinforcement. That's the green line you see that just falls down to zero. Or we can have a residual strength like you see in the curves in blue and red. And that residual strength is coming from the presence of fibers. Obviously, higher amounts of fibers, assuming the same fiber, are going to give you a better performance, or what we typically call a higher post-crack strength. Now, if you look at the ACI 544.4, there's actually a figure that shows you something similar to what I showed you earlier. It discusses low fiber content versus high fiber content. A lot of the application I'll discuss are probably closer to the low fiber content, But the more you add as far as fibers, the better performance you get post-crack. Remember, it doesn't affect your modulus of rupture, it only affects your post-crack performance. If you add higher dosages of fibers, you typically get into a hardening branch, as you can see there, where the strength post-crack is actually higher than the cracking strength. Okay, now I'm going to show a video looking at the bottom of the beam just to show you how this ASTM 1609 test is performed and how the concrete or the point where the concrete cracks when it reaches maximum, and then the residual strength that you get out of having the fibers. So let me load the video. In this part of the video now, you see the strength increasing. So we hit the peak. After we hit the peak, this is where the concrete cracked on the left. And this is the residual strength that you get post-crack. So this is what we're typically seeing and getting when we use fiber reinforced concrete, as opposed to if you had no fibers, you would basically, as we said, have zero strength and the concrete would just break apart. So picture on the right is no fibers. Pictures on the left is what you saw earlier, where the fibers held and gave you a post-crack strength. So this is what we typically get out of ASTM 1609. Now let's just look at the single curve just to explain some of the terms that we're going to use as far as design. So looking at this curve, if you take the area under the curve, this is known as the toughness. If you use the toughness and basically average it out, you can get a value that's in PSI or MPa that's known as Fe3. So that's the equivalent residual strength. We typically use this value only for continuously supported members like slabs on ground. There's also a value that's called FD150. And according to ACI 544, this value would typically be used for designing members which don't have any continuous support. So, for example, walls. Now, these are the two main values to use. Many of you that have seen fiber reinforced concrete might have also seen a value called RE3. So RE3 is technically the same value as Fe3, in that it's Fe3 divided by the modulus of rupture. So it's kind of giving you very similar information. The only difference is that RE3 is a value that's in percentage. It's in percentage of the modulus of rupture, rather than Fe3, which is a value that's either in PSI or MPa, depending on your unit. Now, the way the industry is going, we're tending now to use more Fe3 than RE3, but you'll still find RE3 being used for fiber reinforced concrete. Here are some examples of typical ASTM 1609 data that we've tested. Note here that we don't usually just test one beam, we test several beams, so the minimum is typically 3. Many times we actually go higher because we're concerned about some variability that might occur with the test. But this is how the graph would look, and a typical report would actually look like this, where the dosage of fiber would be reported in green. That's what you see above. And then the FD150 value, that's what you see here as 150, 150, would be reported for each dosage. And then the Fe3 also is reported in the reports for a fiber, and the RE3 value below that, below in orange. So this is typically the type of reporting or testing that we would do to be able to determine the dosage for a certain application of fibers. Now, how are these values useful? Well, the top figure shows you how to calculate moment capacity of reinforced concrete, and most of you are probably familiar with that. The portion below shows you how the capacity of fiber reinforced concrete could be estimated. And note, again, this is based on ACI document 544.4, which is the design guideline for FRC. Now, as you can see in the equation below, that by knowing an FE3 value, which we determined using 1609 testing, or knowing FD150, we can determine the moment capacity or the flexure capacity that we would need for any design purposes. Okay, now as I mentioned, as far as the design of fiber reinforced concrete, ACI 544.4 is going to be the main guide that ACI has, and probably the best resource you'll find out there that will discuss all aspects of designing with fiber reinforced concrete. However, ACI also has other documents that do discuss designing fibers. So one of them is ACI 360, which is a document that's mainly about slabs on ground. And there is a chapter about fiber reinforced concrete, which includes a lot of good information on how to design slabs on ground. Now, before I get into specific applications and discuss design, I just want to make a note that when designing FRC, there are two different concepts that can be considered as far as methods of designs or designing for certain applications. Now, some concrete elements can be designed as plain concrete, where it is assumed that the concrete does not crack due to loading, and therefore the flexural capacity of concrete can be accounted for, and the reinforcement will mainly be used for controlling crack width. Now, different terminologies are used to describe plain concrete design. Sometimes it's referred as unreinforced concrete or lightly reinforced, but these are all the same concepts. They're basically, as far as flexure, based on using the modulus of rupture of concrete. Now, the other concept for designing concrete, which is commonly used for every type of reinforced concrete, is reinforced concrete design. And this is where we assume that the strength of concrete in flexure or in tension is going to be 0. And in this case, the role of the fiber is going to be mostly on the post-crack. It does provide some crack control in general for the structure, but we're typically looking at the post-crack flexure strength we get out of the fiber. Now, if some of you are not aware much or haven't used plain concrete design recently, just note that there is a whole chapter even on ACI 318 about plain concrete design. That's chapter 14. And that chapter actually tells you which members can be used for designing plain or can be designed as plain concrete. So you can see I've highlighted that in orange, and that includes members that are continuously supported by soil or supported by other structural members. You see it talks about walls, pedestals. So that's just a small amount of actual applications that can be designed as plain concrete, but this is what's typically allowed as far as buildings. Okay, now let's get into specific applications, and I'm gonna talk now more about slabs on ground. Slabs are typically designed for loads such as vehicles or post loads. That's what you see the forklift on there. This is typically what we would use to determine the thickness of a lot of the slabs if we're doing plain concrete design, and I'll get into that example. We also design slabs for volume change load. So this is your expansion and contraction. All these have to be taken account when designing slabs. Now, if we were to take into, as an example, a plain concrete or a lightly reinforced concrete, we typically take care of the issue of volume change by specifying certain joints length, which are based on shrinkage of concrete. So the figure that you see is actually coming from ACI 360R. It's figure 6.6. And most of the times when we're designing slabs on ground, we pick our joint spacing depending on the type of concrete that we're using. So if you're using a high shrinkage concrete, we typically don't go above 15 feet as far as joint spacing, assuming, again, you're designing an unreinforced plain concrete or lightly reinforced concrete slab. Now, to be able to pick the value and know, first of all, you probably have to determine the thickness of the slab, and that's going to be a function of the type of loading that you have. But this is typically what we would be using for designing slabs on ground, is determine thickness using knowing what the load is, and then determining the joint spacing, knowing what type of concrete we have. What we typically end up with is reinforcement that's placed at the top of the third or in the top third portion of the slab. The reinforcement that would be used for a lightly reinforced slab or a plain concrete slab is typically 0.1%. We don't have to use more for this type of application. And this amount of reinforcement also should be what goes through the joint and not more, because if you have more than 0.1%, the joint might not activate. And that could be an issue where you could start getting cracking that is out of joint cracking. Note also that we sometimes add dowels. Dowels are there to transfer shear between joints, and they're typically used whenever we have heavier moving loads on the slab. Okay, now the same application that we saw with reinforcing steel can also be done with fiber reinforced concrete. So if you're doing a plain concrete type design, you can use the exact same concept we used earlier, determine your thickness using the modulus of rupture. And then as far as minimum reinforcement there, the typical dosage would be based on an Fe3 of 100 psi. So for macrosynthetic fibers, that's typically anywhere between 3 and 3.5 pounds per cubic yard, or around 1.8 kilograms per meters cube. If you use a higher dosage than that, then the typical recommendation is to have a deeper joint, so D over 3 instead of D over 4 as far as how deep the joint is. And the reason for that is to make sure that the joint actually activates and you don't get out of joint cracking. Now, an important note here is that if you calculate the shear capacity of fiber reinforced concrete of even the uncracked section, and you compare it to the shear capacity that you're getting out of the dowel, you'll see that no matter how much fibers you add, it's hard to get the performance that equivalent as far as shear transfer to what you're getting out of a dowel. So that's why typically we don't recommend replacing or removing dowels when using reinforced concrete. So just to make it clear, if you're substituting steel with fibers, you typically do not remove the dowels. You keep the dowels. The fibers are not replacement for dowels. Okay, now I showed the example earlier of a plain concrete section. If we were to do a reinforced concrete section, we would typically use the top reinforcement at a value that's above 0.5% if we're trying to get rid of joints. So that will be reinforcement that's used for controlling crack width at the top, and that's typically the percentage that's used. As far as the reinforcement in the bottom, it might be used to increase the flexural capacity of the concrete. So that's where we would assume a cracked section at the bottom and then put as much reinforcement at the bottom as needed to resist or to provide us with the strength we need at the bottom. For fiber reinforced concrete, we can actually do the same thing. But in this case, we would have to add a much higher amount of fiber than we did originally. So in the case of the unreinforced concrete slab, your Fe3 value, as I mentioned, is around 100 psi. We typically see anywhere between 100 and 200 for the unreinforced cases. When we get into trying to control cracks and have less joints and provide flexural capacity using the post-crack strength of the fiber, our values are usually for Fe3 above 200 psi. Now, I'm not going to get into a design example in this presentation because there's not much time to get into the details. But if you're looking for an example on how to design for flexure, currently there's an example in ACI 360R, Appendix 6. The example does say that it's for steel fibers, but it's actually also applicable to synthetic fibers because it's based on performance. So that example is using RE3, and as long as you meet RE3, whether you're using a steel or synthetic fibers, you'll be fine. Okay, now knowing the performance that we got, the value, we can use it in our project specification to inform the concrete producer on how much fiber is needed. So instead of putting a dosage, you can put an Fe3 value and use language similar to what I have on here. Now, just a small note in bullet point number 2, you see a reference to ASTM C1812. So the new version of ASTM 1609, or one of the more recent versions, requires the use of a certain type of roller. These are defined in ASTM C1812, and this type of roller was not required in the past. Now, the reason this is important is if you had these rollers or didn't have these rollers, you might get different values. So if you're reviewing any type of ASTM 1609 testing, please make sure that they were done using the new standards and that the 1812 rollers were used, and make sure you don't compare these values to different values where these rollers were not used. The absence of the rollers does give some advantage as far as testing. They might give some higher values, and they might be overestimating the performance of the fiber. Okay, now moving on to concrete slabs on metal deck. So concrete slabs on metal deck are typically designed using a standard that's called the Standards for Composite Steel Floor Deck, SDIC. And the way you know that is if you open ACI 318 and you look at chapter 1, which is the scope of the document, it tells you that ACI 318 is not the code that applies for this type of design. There's a different standard to go to, and that's the standard that you see on here on the right. So it's the Composite Steel Floor Deck Slab document, and the last version I've seen was released in 2017. Now, this standard tells you that fibers can be used for temperature and shrinkage crack control, as you can see in yellow. So you cannot use fibers, whether they're steel fibers or synthetic, for resisting any type of flexural stress or shear stress. They're only allowed as far as temperature and shrinkage reinforcement. This code also sets a limit, and as far as synthetics, you can't go below 4 pounds. So it tells you that the dosage would be determined by the fiber manufacturer and shouldn't be less than 4. So 4 is the minimum that would be allowed as far as dosage. If you're putting this in your project specifications, you can use the same language I showed before. So bullet 1 and 2 are the same as what we used for slabs on ground, but then you can add a bullet number 3, which says that the dosage cannot be less than 4 pounds per cubic yard or 2.5 kilograms. Okay, this is as far as I'm going to discuss as far as design. If you have more questions, please send me a question in the chat, or you can contact me anytime and I can provide you with more details about using fibers for other type of designs. Now, one important thing I want to note at the end of this presentation is how fibers affect concrete mixtures. So the pictures that you see in front of you are pictures of fibers before and after mixing. And as you can see, the fibers don't look as good as they do after they're being mixed, as far as they probably would require a lot more paste to coat them. So as far as workability and finishability, that's something that's very important to note, that you have to have enough paste to be able to get these properties. Obviously, you need the paste to make sure that the fibers are all glued together properly in concrete to get the full performance. But typically, you need more paste to get the proper workability and finishability that you desire for a certain application. So if you're using fiber reinforced concrete, make sure that the concrete producer has experience with using the fiber at the required dosage. If this is the first time that they're using it, make sure that they test it first, so they conduct some testing. Make sure that the mix design is correct. If not, they can adjust it. And you can also have a requirement to have a mock-up to make sure that what gets in the field is actually what you're looking to as far as performance. Now, note that typically a fiber manufacturer would be the one advising the concrete producer on any type of mixed modification needed for a fiber. So that's not something as a design engineer that you have to worry about. It's typically a fiber manufacturer would know that if they're using 5 pounds versus 7.5 pounds, they need a certain amount of paste for that application. Last thing I want to bring up is a question that is coming up now more recently, is that are synthetic fibers sustainable compared to reinforcing steel? So as you might know, the topic of sustainability has become much more important. And one thing that's always noted is that the global warming potential, or GWP, factors of synthetic fibers, when you look at them basically pound per pound or kilogram per kilogram, are 4 to 5 times higher than what they are for reinforcing steel. So what I mean is, if you look at the GWP factor for 1 kilogram of synthetic fiber versus 1 kilogram of reinforcing steel, the synthetic fiber is going to be higher. Okay, but just looking at the GWP factor doesn't give you the full picture. When we're looking at using them on a project, you have to also account that the quantity of synthetic fiber that is being used as compared to reinforcing steel is much lower. So to make more sense of this, I have an example. So assume you have a 6-inch slab on ground, reinforced with number 3 at 18 inches in each way, so in each direction. So that's around 0.1%, similar to what I talked about earlier. If you calculate how much steel would be in that slab per cubic yard of concrete, the value I got was 27.1 pounds of steel per cubic yard of concrete. Now, this amount of steel, if you were to replace it with synthetic fibers, would be around a 3-pound replacement. Now, if you compare 3 to 27, that's around 9 times less material than what we used as far as steel. So yes, the GWP factor might be 4 to 5 times more when you're looking at pound to pound, but then you're using much less materials as far as the final application of the concrete. So with that, I'll conclude the presentation and open the floor for questions. Aparna?
Yeah, hi Mark. Yeah, we truly appreciate your exceptional presentation and for generously sharing your wealth of knowledge and perspectives with us today. So let's move on to our question answers. So our first question is, how do you control the bunching of fibers within a mixed design? How can you ensure that the fibers are evenly distributed?
That's an excellent question. So depending on the operation, whether we're talking about a cast in place or a precast, that's something that's going to be particular to them. But it's typically important to note where and when fibers are added. The best time typically to get the best dispersion is to add fibers with the aggregates. That will give them some shearing action and break them apart and have them get dispersed in the concrete. So if you need more question about the specific fiber, always ask the manufacturer. They'll typically give you what recommendations work best. That's in general if you're not sure about how to use certain fibers.
Yeah, got it. So our next question is in line. It's good you gave an explanation about the steel fibers and the synthetic fibers. Our next question is, like several research studies have shown the use of steel fibers for earthquake-resistant structural elements, particularly in plastic hinge region. Is there any result regarding the use of synthetic microfibers for the earthquake-resistant structures elements?
So for earthquake, I don't think I've seen research. I've seen recently some work on blast. But we can definitely look into it more and provide them with some references. We don't typically see that usage. That's very common. It might be something obviously that's there out as far as research, but for common application, that's not something that's very common.
Okay, yeah. Our next question is, what is the optimum dosage of synthetic micro and macro fibers?
So again, good question. It depends on the fibers. So if we're talking about an application, for example, like a slab on ground with micros, As I mentioned, with monofilaments, you're typically between 0.5 to 1.5 pounds per cubic yard. For fibrillated, it's 1.5. That's a typical dosage. For macros, on these applications, you can be anywhere from 3 to say 14 pounds per cubic yard, again, depending on the need. Typically, most of applications we see out there are between 3 and 7.5, but there has been exceptions where they've gone up to as much as 14. Now, again, this is going to be dependent on the type of fibers. With some fibers, because of paste requirements, you might not be able to go above 7.5. So there might be a practical limit as far as making the mix.
Yeah, got it. Our next question is regarding the estimate weight, but yeah, do you have any rough estimate what percent we can save in weight of the structure or steel bar utilization in the simultaneously usage of reinforced concrete and synthetic fibers?
So typically we don't see any much of a change in weight. Remember that the amount of reinforcement that we're adding in a lot of these applications is very small as far as volume. So overall weight of the concrete is not something that we would account for. So as far as design, we would use the typical numbers that are used for reinforced concrete, nothing less.
Mhm. Yeah, our next question is regarding the standards. Yeah, have there been any significant changes to industry standard materials in recent years? I ask because of an experience with a 90s building using FRC with macro. Sorry, the question is, yeah.
Okay, I think I can answer the question. So
Mm-hmm,
yes, there actually is more work being done on standardizing, and I'll mention that ACI 544 has an upcoming specification that's going to be for now limited to slabs on ground, but we are introducing more documents that will have some mandatory language like a specification, and we'll probably even add more as far as design examples to show how to properly design with the materials. Now, some of these design guidelines we add are not code, so they're
mm-hmm,
not required for anyone to use, but they will show what the best practice is. As far as our specifications, we are trying to set some limits. So one of the limits that we will be that will be included in the an upcoming ACI specification on slab is to make sure a dosage of fiber is never less than 100 psi as far as Fe3. So that's one of the main requirements as far as mechanical performance. Obviously, for other type of structures, limits are going to be different and values are not going to be the same.
thank you. Our next question is, you showed a graph showing different performance characterization of FRC, softening versus hardening. Can plastic fibers provide hardening performance? This is
Yes. So at higher dosages and with some fibers, yes, we can see. Remember that the hardening is also a function of what the modulus of rupture is. So if the person asking the question was looking at something like ultra high performance, where you typically have a much higher flexural strength, then you might not see a strength that goes above that. But if we're looking at the concrete in the range of the 3,000 to 5,000 psi, then yes, you might actually see a hardening with a higher value of synthetic. So again, keep it in context of the type of concrete that you're using, and it's something that we've seen, at least with I can verify with the lower strength concretes.
Yeah, when the last question we would like to take is, for cylinders, what would you consider the maximum allowable macrofiber length to cylinder diameter ratio?
So if you just stick by the values I showed earlier, by the values accepted by ASTM D5708, you should be fine with the typical cylinders used with 4x8s. So as long as you're meeting that ASTM standard, that's not something to worry about.
So this ends our question and answer session. So on the screen, you can see the list of upcoming webinars at ACI University. Please visit aciuniversity.com to register. Before we go, I have two more important announcements. Firstly, Next is co-sponsoring two in-person public seminars on designing concrete structures reinforced with FRP bars using the new ACI code 440.11. These are full-day seminars and offers face-to-face interaction with a highly recognized speaker in a classroom setting. It will provide you free resources and referencing tools given for the use both during and after the workshop, along with the opportunity to network with other concrete professionals. So anyone in the Maryland area can attend on September 13th, while those in Florida can join on October 9th. So to register or to get more information, please visit aciuniversity.com/public seminars. Secondly, next request for proposals for 2024 projects is open until September 5th. There are 13 topic project titles available for proposal submission. For more details, visit nonmetallic.org/request for proposals. I hope you all would be able to engage with Next more. Again, thank you for all joining today's webinar, and we look forward to having you with us again in our next webinar. Thank you.